Source didn't state this was an Olympiad problem, but I think it is. Russian Olympiad all the way back in 1996. And I've always enjoyed these problems because I think they're a cut above the standard number theory problems that appear in the United States, number theory textbook, undergrad. A lot of the ones that appear in textbooks are just made to work. If you know the formula, you can work the problem. These require a little bit of extra thinking. I think in that sense are more challenging than a typical undergraduate number theory textbook. Now you can read this statement. It says, are there three distinct positive integers, each greater than 1, such that the square of each integer minus 1 is divisible by both of the other integers? Okay, that's a mouthful, but we can get that translated into mathematics pretty quickly. And we can do the standard without loss of generality down here. We can order since they're distinct, we can say A is larger than B, B's larger than C. So WLOG, the infamous without loss of generality. That's not that restriction doesn't interfere with the generality of the result or the truth of the result. Now, let's keep going. Now, this is very important. It took me a while to figure this part out, as simple as it is. This part right here, it says B divides A squared minus 1, and that's just the given, right? The square of each integer minus 1 is divisible, and that's what this statement says. You guys will notice this vertical line means divide. It's a divide operator. This guy right here is a divide operator, if you will. Now, this part right here is easy, but it took me a minute to get it. If B divides A squared minus 1, that means A squared minus 1 can be written as KB for some other integer K. That implies that A and B are what they say relatively prime. That these guys right here are relatively prime, A and B. Notice it doesn't say A squared. And it's real simple if you just take a look at this. Now I'll just write it underneath here. If A is odd, okay, if A is odd, that forces B to be even, and conversely, okay. If A is odd, B is even. Why is that? Well, if you just take a look at this statement, it's fairly clear. Meaning, right here, let's say A is odd. If A is odd, A squared is also odd, and if you subtract 1 from an odd number, you get an even number, right? So that means that B has to be even, okay? And so this goes in both directions. So the mere fact that B divides A squared quantity minus 1 intimates that A and B are co-prime. This is, I say relatively prime, I've heard it called co-prime. Okay, that's a very common usage these days. Relatively prime was the phrase they used when I was taking this a long time ago. All right, so now why is that important? Well, let's go on down and take a look here. We also have this statement right here that AB divides the quantity C squared minus 1, and again, that's just the problem statement. For all three of the numbers, we have this kind of symmetry going on where we have AB dividing C squared minus 1 in this case, okay? Now, what does that imply? Okay, well, this original statement right here, this original statement, A greater than B greater than C, implies AB is greater than C squared, and you can see that's crystal clear. This statement right here is certainly true based on our assumption at the beginning of the problem, but this part right here also implies that AB AB is less than or equal to the quantity C squared minus 1. Okay? You see right here, we actually get AB is greater than C squared. Well, that's certainly a contradiction, all right? So we have a contradiction. And what does that mean? That means that this condition can't happen. It's impossible. Okay, so the answer to the question would be no. Okay, this is a contradiction. And that means we don't have three positive integers that could satisfy those restrictions. Okay, contradiction, T-I-O-N. Okay, so y'all, that does it. again, so the answer to the question would be no. All right. So anyway, I hope you guys enjoyed that. I liked it. And again, I want to repeat, I think these Russian problems are very creatively made. I mean, whoever makes these kind of problems up knows a lot more about number theory than me. You know, you don't typically see these kind of problems, you know, in a standard number theory textbook. So it's pretty interesting, somebody sitting down thinking up something like this, you know. Now, if you're interested in looking at just a concrete example, let's say that we had if we picked, what do we want here? We can pick, let's say, let's take A to be 9, let's say. All right. Well, then we can see that A squared minus 1 okay, is equal to 80, right? And notice that 9, that's equal to 80. Sorry, folks. That's equal, let me erase that. This is 80. Let me get that part erased. All right. So this is 80. Now notice that 80 doesn't have any factors. 9 is not a factor of 80. So 9 does not. And this is just one special case, but 9 does not divide 80, right? Okay, so that's kind of interesting. I mean, that's just one example. You know, that's just one example, and it doesn't prove it. But this part that we just did right here conclusively proves it. This part actually sort of is related to the relatively prime piece that I talked about a moment ago. But in any event, we did reach the desired contradiction, and we can emphatically say that no 3 integers like this do not exist.